Okay, here we go. All right, all of you can see the PDF slide. Can all of you see the slide? Okay, good. Okay, guys. So now we are in the second lecture for phase transformation. All right. Last week, no, not last week. Previous session. Oh yeah, remember to record. Thanks, Nicholas. Luckily, you have mentioned this. Okay, it's recording now. Thanks for reminding, Nicholas. Okay, guys. Last week we have gone through. No, not last week. Previous session we have gone through this phase diagram, the basics of phase diagram, and I did mention to you there are some structure, what is solvent, what is system, and we have a few types of phase diagram: unary, binary, okay, eutectoid, two component system, and so on. And how do you interpret this phase diagram? Okay, binary, eutectic, and so on. And then this is binary isomorphous. And then we have let's see over here. Okay, this is liquid, this is solid, and this is liquidus line over here. This is liquidus line, and this is solid line, solidus line we call that. That's the one that separates between liquid and solid. Between the liquidus line and the solid line, you have a mixture of liquid and solid. Okay, please recall that. And how do you going to find the composition of liquid and solid if it falls under this region? If it falls under this region, how do you going to find the composition? You can find the composition by utilizing tie line. Remember tie line? Draw a horizontal line that touches the liquidus and solidus line. Just go down and you can find the composition. If you find the fraction, you need to use the lever rule. Okay, this is the fraction. Okay, just a quick recap for lever rule. For example, this is your initial composition with CO at 1250 temperature, and the question asks you what is the weight of this material when the temperature is at 1250. What is the weight fraction of liquid? What is the weight fraction of alpha solid? So what you need to do is draw a tie line. At first you can find the composition, then when you want to find the phase weight fraction, you use lever rule. This is R, this is S. Last week I remember there's one student asked me what is R, what is S. I have no idea on that. You can name whatever name you want to name it, okay? It's okay with that. But the concept, you need to know the concept, okay? So if you want to find the weight fraction of solid, okay? So this is solid, weight fraction of solid. You need to take the values of R, which is CO minus CL. Okay, CO minus CL divided by the whole composition, which is CS minus CL. Here you go, CS minus CL. Okay, and then subsequently, if you want to find the weight fraction of liquid, which is over here, you need to take the S divided by the whole composition. So S is CO minus CS. CO minus, where is it? C? Sorry. It is supposed to be the from high to low, sir. CS minus CO. Here you go. CS minus CO divided by CS minus CL. CS minus CL. Okay. So that is how you utilize the lever rule, and then all these equilibrium cooling and how does the formation of grain works. Okay, this just you can just read this through. And the mechanical properties, when you add more nickel, what will happen to the tensile strength and elongation? You have a percolation threshold over here. And eutectic system, what is eutectic, what is eutectoid, and so on. Okay, this is eutectic. And eutectic system, this is alpha, which is a pure dominance. Here, beta, which is another pure element dominance. So it is being separated by most end of your horizontal line. This end is pure substance. Here is also pure substance. And this region is the mixture of those substances. So it is well defined. Okay, it is well defined for binary eutectic system. Okay, here you have 100% copper. Here you have a 100% argentum, which is tin. Okay, silver. Okay, silver. Tin is Sn, stenum. Argentum is tin, silver. Sorry, Sn, silver. Okay, so it is well defined, the pure substance over here. But for today's lesson, guys, so I can just keep this eutectic. For today's lesson, I will be concentrating on one particular phase diagram, which is ferrum and then cementite diagram, which is ferrum, iron ferrum, iron carbon phase diagram. We call that as iron carbon phase diagram. This is ferrum, which is iron, and Fe3C is cementite. We call that as cementite here. It is a binary eutectic phase diagram, but it is in your syllabus due to the fact that if you look at this phase diagram over here, you can't see a distinct pure material. You can't see a distinct pure material which is on the both end side. Okay, so this is quite complicated. And here you don't have any 100% of carbon. Can you see? Whereas all the examples before this, you have 100%, right? Here 0 and here 100%. And the pure materials stick to the portions on their side vertically. But if you look at iron carbon phase diagram, 6.7% only. So it means that yes, you have 7%, 70% and 100% here, but it have been chopped off because all those are graphites. Why? The reason is because this is the most useful phase diagram in our current society, because we are living in a metal age, and metal age, and we will be utilizing a lot of ions. We will be utilizing a lot of alloy ions, which compose of iron and also carbon. So in this phase diagram, which is a composition of iron and carbon content with a maximum of 6.7 percentage. So over here you can add a lot of alloying element into iron, and those alloying elements are carbon. So you can create a lot of materials. That's the reason why you have a lots and lots of carbon iron in the market. You have Japan standard, you have American standard, you have Malaysian standard. It's almost infinite. A lot of things. Okay, now let's digest this phase diagram one by one. Okay, so what is my understanding is, okay, pure iron over here, only this line, this vertical line, only this vertical line, this is your pure iron. Okay, this vertical line only. Here you have a carbon content of 6.7 percentage. This is not pure copper. So this is not pure carbon. Okay, sorry. This is not pure carbon. This is what we call as cementite. Okay, it is a mixture of iron and carbon at roughly at a weight percentage of 6.7. That is the reason why there's a lot of confusion. They don't call iron carbon phase diagram. They call it iron cementite phase diagram. You can call whatever name you want. Same goes to R and S, the lever rule. Okay, you can name it whatever name you want. But here there's also a confusion among societies. Some of them will call them iron carbon system, but the carbon here is not 100%. It is 6.7. Some of them will call it iron cementite diagram, phase diagram, just because it is not 100%. Okay, fair enough. Huh? Okay. So in this, okay, we call that, for the sake of this lecture, we call that as iron carbon phase diagram. So in this iron carbon phase diagram, you have few microscopic structures of iron in addition to carbon. Okay, we have alpha, which we call that as ferrite iron over here, which has a maximum solubility carbon content of 0.22. Write this down, guys. We have alpha ferrite iron, okay, alpha ferrite iron, which has a maximum solubility of carbon at 0.022, which is over here. Above 912 degrees Celsius, all right, above 912 degrees Celsius, pure pure iron will transform into austenite microstructures iron, okay, from 912 degrees Celsius up to 1394 degrees Celsius. Okay, it is in austenite microstructure. For your information, alpha or ferrite iron composed of FCC. Okay, austenite, we call that as gamma, and it composed of BCC. Okay, ferrite, very low carbon of FCC, BCC, austenite, interstitial solid solution carbon of FCC crystal structure. Okay, cementite is intermetallic compound which is hard and brittle, and it is in metastable state. Okay, and then we have another one, ferrite. Here, over here, ferrite. We call this here as ferrite, which is above 1394 degrees Celsius. It has a, it is in BCC crystal structure, and the solubility is 0.09%. Over here, 0.09% over here. This is the maximum solubility. Okay. Hold on, guys. Hold on, guys. Okay, yeah, correct. Okay, guys. So the first one is ferrite, very low solubility of carbon in BCC crystal structure, maximum solubility at 0.02 over here, maximum solubility of 0.02 ferrite. Okay, and then we have austenite, which is interstitial solid solution of carbon in gamma iron. It is under FCC crystal structure, and the solubility is 2.8 percentage 2 at 1148 degrees Celsius. 1148 degrees Celsius, where is it? 48, somewhere around here. Solubility, this is the maximum solubility. Okay. And then we have, it is non-magnetic. Ferrite is magnetic. Okay, this is just the properties. And then we have cementite towards this end over here, which is over here, this end, cementite. Intermetallic compound, hard and brittle. Just for the rule of thumb, the more carbon in an ion, the more brittle and higher the strength the ion is. Okay, so it is hard and brittle, which composed of 6.67% of carbon and 93.3% of iron, and it is metastable. Okay, so this is the maximum carbon that can be added into an ion. And then we have ferrite. BCC crystal structure, maximum solubility at 0.09 at 1465 degrees Celsius over here, and stable at high temperature. Okay, over here, this region. Okay, so we have few types of microstructure of iron depending on the temperature. Okay, and when you add the carbon content, composition of carbon, this alpha ion will becomes alpha cementite, iron cementite. Okay, iron plus cementite. As the temperature increases, ferrite, so these are ferrite regions, guys, this is ferrite region. As the temperature increases, pure iron changes its phase into austenite microstructure, which is FCC. And when you add more carbon into it, it's become austenite cementite. Further higher the temperature, we have a liquid region when the carbon content is above 2.14 at 1147 degrees Celsius. So it is in the semi-liquid phase. Below the content of 2.14, it is still in solid. Okay. So the solubility limit for austenite is 2 point. Okay. Okay. By just looking at this phase diagram, iron carbon phase diagram, there are a few points that I can phase out. The first one is peritectite reaction. Okay. Peritectite reaction is a reaction where a solid phase and a liquid phase will together form a second solid phase. Okay. Liquid phase at it is happening in the delta region, which is ferrite BCC over here. At 0.53 carbon content. Okay. When you reduce the temperature, it changes to austenite. Okay. When you reduce the temperature, it changes to austenite. When you increase the temperature, it becomes two different distinguished microstructure, liquid phase and solid phase. And then you have eutectic reaction, okay, which is in 4.3 and 1148. 4.3 and 1148, 1147. Okay, over here, eutectic. This is eutectoid, solid to two different phase of solid. Eutectic is from liquid to solid transformation, or from solid to liquid transformation. Eutectic, liquid, you cool down, it becomes two different distinguished microstructure. When you heat this, it becomes liquid. Automatically it changes to liquid without any transformation to liquid and solid. Okay, it is from solid directly to liquid over here, this point. Okay. if your composition, if your carbon content, let's say your carbon content is 4, when you reach the temperature of 1147, it melts to liquid and austenite first, not pure liquid. After you increase the temperature to roughly, this is 12, okay, 11, so 19 something, then only it changes to liquid, okay, fully liquid. This is semi-liquid. But in eutectic reaction, fully liquid substance can change to fully solid within a temperature range of 1147 degree Celsius. Okay, and we have eutectoid reaction. Okay, eutectoid relation is an alloy which has a minimum transformation temperature between solid solution and simple mixture of metals. So between metals and two different types of metals, or between solids, pure solid, to two different types of solids, eutectoid reactions. Here 723 0.8, 723 0.8 over here. Okay, eutectoid, eutectic, and then we have peritectite over here. Okay, and in eutectoid steel, I'll be concentrating on eutectoid steel. Any alloying or any addition of carbon less than 0.8 percentage of carbon, we call that as hypoeutectoid, less carbon. An addition of carbon more than 0.8 percentage into iron, we call that as hypereutectoid steel. More, the stronger it is because of carbon content, but the melting temperature reduces. Less, the ductile it will be, but the melting temperature increases by just looking at this phase. More, the melting temperature reduces. Lower, the melting temperature increases. Okay, but the effects will be lower carbon content gives you softer material. Higher the carbon content, the harder the material it is. Okay, so if you look at the microstructure or morphological microstructure of iron carbon steel, this is alpha ferrite and this is austenite. Okay, austenite is more prominent. Alpha ferrite is more random. Okay, and alpha ferrite is in this region, less carbon over here, ferrite. And this is austenite, stable at higher temperature. Okay. Okay, guys, can you understand until now? It's quite complicated. It's quite complicated. A lot of these austenite, pearlite, martensite, cementite, you name it. Okay, there's a lot of terms that need to be known. Can you understand so far, guys? And any questions? Any questions on the iron carbon phase diagram?
So can you repeat the peritectic and the eutectoid?
Guys? A bit confusing. Okay, okay. Which part? Which part? Let us clarify. Let us clarify. Don't worry. Which part you don't understand? Can you repeat peritectic and eutectoid? Okay. Okay, Lua Wenzheng, peritectic and eutectoid. Clement, which part? Okay, peritectic reaction. when you look at peritactic reaction, the thing that you can have in your mind is a transformation of semi-liquid austenite into solid austenite. Two different distinguished semi-liquid material becomes one distinguished material, solid material. That is peritactic. Okay, liquid having two distinguished material phase microstructure, which is we have this delta ferrite and also liquid, pure liquid, what they call that iron, and also ferrite BCC, what they call iron. When you reduce the temperature, it becomes austenite. Okay, it's over here. When you reduce the temperature, it becomes austenite here. Okay, and vice versa. In austenite, when you have a carbon content, a particular carbon content of 0.17, when you increase the temperature, okay, the carbon content is fixed 0.17. When you increase the temperature beyond 1957, 1497, it transforms directly into liquid having a carbon content of 0.53 and ferrite iron, which has a carbon content of 0.09 carbon over here. It transforms directly. So that is the definition of peritactic reaction. Okay. When a solid phase, one type of solid phase and a liquid phase bonds together to form a single solid phase. Okay. Different phase, you have two different phase, liquid and solid, bonds together to become a single solid phase. Eutectic reaction, pure liquid phase, when you cool down, it changes into two different phases. Okay, eutectic is here, pure liquid, it changes into two distinguished solid without going through semi-liquid, what they call that transformation. From liquid directly to solid, in an instant. But you need to have a carbon content of 4.3. Okay, carbon content of 4.3. For peritactic reaction to occur, you need to have a carbon content of 0.17. And then eutectoid reaction happens here. You need to have a carbon content of 0.76. From here, solid, this is solid. From here, you change phase to two different distinguished solid transformation. 0.78. Okay, you can go for 0.8 or 0.76. Okay, it's almost identical. You reduce the temperature, it changes to two different phase. Solid, from solid to solid. But two distinguished phases. Okay, you have alpha ferrite, which is BCC, and then you have cementite as well. Okay, can you understand? Luo Wenzheng, Clement? Peritactic, eutectoid, and eutectic sounds similar, but don't confuse by the sounding. Okay, so how to know the percentage of carbon in those mixture? They will always give you in the questions. For example, peritactic reaction only occurs when the percentage of carbon of 0.17. Okay, and eutectic reaction only happens when the percentage of carbon at 4.3. Eutectoid only happens when the percentage of carbon is 0.8. Okay, by looking at the phase diagram over here, 4.3, This is 0.76, which is 0.8, and this guy is 0.17 over here. Okay. Is the carbon content percentage in invariant reaction more important, or the temperature is more important? Carbon content is fixed. Okay. Temperature and carbon content for invariant reaction is fixed. That is the properties of the material. It is not invariable. It is not variable. It is fixed. So where is the liquid 0.53 carbon content at? Where is the liquid 0.53 carbon content at? Let me see. Oh, over here, 0.53 carbon content. Okay, here, this phase, here, this region. Okay, and then this region, this point here is what you call as peritactic reaction. Okay, the definition of peritactic reaction is a solid phase and a liquid phase. Okay, both solid phase and liquid phase together form a second solid phase. They form a second solid phase, which is this pure solid. Here, having a solid and a liquid. Okay, solid and a liquid. This is pure liquid. Okay. Clement? Okay. Loa? Yeah, thanks, sir. Delta ferrite, okay, is peritactic reaction is a solid. Yes, yes. Delta ferrite in peritactic reaction is a solid. Yes. It changes to austenite. At first, it is quite confusing because of the terms. But what do you do, guys? Try to digest the temperature on the phase diagram. When you reduce the temperature, everything will be cooled down to solids, right? So this is solid. This is solid. This is solid. All of these phases are solid. This is semi-liquid over here. Semi-liquid, semi-liquid, pure liquid. Higher the temperature. Okay, these are all pure liquid. Semi-liquid. Okay, so think of that in mind and imagine if you're reducing temperature, what will happen? From here, reducing temperature, it is still you're still going to change from austenite to and liquid, and then it becomes austenite. Here, you have a transformation of this liquid and also ferrite. Liquid and ferrite, it becomes austenite directly. Okay. This region, guys, this region is still ferrite, same as this ferrite. It is more stable at this temperature. This is ferrite. Here, we call that delta ferrite. BCC crystal structure, maximum solubility is 0.09 at 1465 degrees Celsius, stable at high temperature over here. This is still ferrite, BCC. This is also ferrite, but this ferrite is alpha ferrite, BCC. Okay. And austenite is FCC over here, austenite. Okay, guys. So liquid mostly on top of part. Yes, yes. Liquid. All the phase diagram. The most top of the phase diagram is liquid. Higher the temperature. Don't get confused. This is also a phase diagram, but for this phase diagram, I'm focusing particularly in iron carbon phase diagram. So the iron carbon phase diagram looks like this. This is iron carbon phase diagram. Previous lecture, for example, what is this? Lead and tin phase diagram. It looks like this. So this is how you, okay, this is all liquid, right? So see, top of your phase diagram, all is liquid. When you cool down, it changes to semi-liquid. But here, eutectic reaction, eutectic invariant point, eutectic point, liquid directly to solid. But here it is more complicated. Where is it? Here is more complicated. Okay, you have this eutectic point here as well. Just that you get confused by a lot of points, and you have a lot of terms here as well. So in order for you to master this iron carbon phase diagram, you need to listen to the lecture again, and you need to understand this again and again. Then you can master this easily. Actually, it is easy. Just that so much. I remember I told you phase diagram, a lot of information that you can get from a phase diagram. So this is one of the classic example that I can show you. So much of information that you can learn. Okay. Okay, guys, so far clear? We are getting late. I don't think we can finish by 11:30. Are you okay, guys? Can you understand until now? Okay, good. So I'll continue. So okay, now transformation of eutectoid steel. Okay, now there's also hypo-eutectoid less than 0.8 and hyper-eutectoid. So now let's look at eutectoid steel 0.8, which is 0.76. Okay, so at first I have a material, iron carbon, having a carbon content of 0.8, and I'm going for a rapid, not rapid cooling, slow cooling. At first, it is under austenite. Solid. It is still solid. It is still solid. Don't think this is liquid. This is still solid over here. Austenite is solid. Okay. When I was young, during myself as a student, I used to think this is liquid. I made this kind of mistakes. So this is still solid. It is predominantly in FCC, austenite. Okay. As I cool this, it changes directly to ferrite, cementite. So the composition is nice and clean. Ferrite. Okay, as I cool this, and then you have austenite over here, and then this is alpha, which is ferrite, and then this, which is your what they call that cementite, carbon. And we call this as pearlite. Okay, I read somewhere else they call this pearlite because the shape of this looks like a mother pearl. Mother pearl, I don't know what is that. What do they mean by mother pearl? I think there's a type of natural pearl. When you look at the microstructure of the natural pearl from oyster, right, from pearl, I'm not sure. It looks something similar like this. So that's the reason why they call it pearlite. So the diffusion is directed. Direction of carbon diffusion is indicated by the arrows. Growth of pearlite, austenite, and then ferrite, and then you have cementite, ferrite, cementite, ferrite, cementite, ferrite, cementite. And under microscope, it looks like this. Eutectoid steel shown pearlite microstructure consists of alternating layers of alpha ferrite, the light phase, and ferrite, thin layers appears dark. Okay, now what happens if I have a carbon content which has less than 0.8? We call that as hypo-eutectoid steel. For example, look at this. Look at this zoomed phase diagram. At temperature around 800, 900, 890, I have a carbon content of 0.4, which is hypo-eutectoid. As I cool down, austenite region, solid austenite, okay, it changes into austenite and what they call that, what is this? Ferrite, yes, ferrite. Okay, it transforms into ferrite first. A small changes happening in ferrite. When I cool further, this ferrite expands further. Okay, bear in mind, I don't have the formation of what they call that cementite. Okay, because if you look at this region, here is cementite, right? This is austenite. This is austenite plus ferrite. Okay, so we are here, austenite and ferrite. Austenite and ferrite over here. So there's no formation of cementite. At first it is austenite over here. When I cools down further, there's a formation of ferrite. Cools further, the growth of ferrite. Ferrites become bigger. When I cool further, it goes to the formation of cementite, the blue one. So this phase is ferrite, and the growth of ferrite at first, we call that as pro-eutectoid. And then you have a growth of eutectoid as well. A new eutectoid is being formed. And then the formation of cementite as well when you cool it further. Remember, this is equilibrium cooling. Okay, slow cooling. Okay, equilibrium cooling. Okay, now what happened if I add a little bit more carbon content above the eutectoid carbon content, which is from 0.8 to 1.2. So the temperature I set it to 900 degrees Celsius. At first, you have a formation of austenite. As I cool down, it reaches to this region. So this region is over here. So that is, you are having a formation of austenite plus cementite. So automatically, you should know that there's a formation of cementite into it. See, cementite is being formed. Ferrite haven't formed yet, and you cool down further beyond the temperature of 727, you will have a formation of ferrite. So this is ferrite. You have eutectoid cementite. You have pro-eutectoid cementite, which has formed before. Okay. Okay, guys. There's a question. So perlite is ferrite and austenite in layer by layer. Yes. Perlite is a ferrite and austenite in layer by layer. Symmetrically, yes. Is symmetrically, sorry. Lower Wenzheng, yes. Layers by layer, symmetrically. Okay. Can you understand, guys? Okay, now for you to, okay, what is the difference between pro-eutectoid and eutectoid? Okay, pro-eutectoid is the formation of, yeah, pro-eutectoid, if you see here, pro-eutectoid is a formation of earlier ferrite. Here you have ferrite, right? These have formed first. And then after that, you cool it further, you have another formation of eutectoid, which is a new eutectoid, which is this. The earlier one, we call that as pro-eutectoid. Earlier, pro, it becomes older, which is much more pro. That's the analogous. Okay, Lower Wenzheng. Okay. Okay, guys. So for the phase weight fraction, for example, when you are here, okay, this is your composition, the same thing, okay, tie ruler. You want to find the weight fraction for ferrite ion. For you to find the weight fraction of ferrite ion, your composition CO minus C alpha, which is your alpha, CO minus C alpha, and then divided by the whole thing, okay? C, what they call that, ferrite, composition ferrite minus weight C alpha, composition ferrite minus C alpha. And then for you to find the weight fraction for alpha, which is ferrite, you take S, which is C ferrite minus with your composition, C ferrite minus with your composition, divided by the whole thing, C ferrite divided by the C alpha, C ferrite divided by the C alpha. Then same, you want to find the weight fraction of your cementite. Okay, if you want to find the weight fraction of cementite, remember here 6.7. Okay, we have 6.7 here, RS. So for you to find the weight fraction of cementite, CO minus C alpha, CO minus C alpha, and then the whole thing. Okay, cementite minus. And if you want to find the weight fraction for this alpha over here, the same thing, you need to use S, which is C cementite, composition of cementite minus with composition of your original material, divided by composition of cementite minus with C alpha. Composition cementite minus with C alpha. Okay, same goes to this as well, hypereutectoid. For you to find composition of cementite, RS, okay, you can do this, right? Okay. All right, guys, any question? Any questions until now? Any questions, guys? Because I can't continue, but just that we have a tutorial class later on, so I don't think that I'll continue this next week Monday. So next week Monday I'll continue this and following with the new topic. Not Tuesday, sorry, Tuesday. Midterm cover this chapter until last slide. Yes, until this last slide. So tutorial for this will be next week. No. Quiz won't focus on this chapter because supposedly I need to finish this chapter today, but we don't have time now. So quiz will be focused on next week's chapter, which is chapter 6. Okay, which is this chapter 6. Thermal processing and heat treatment. I'll be uploading these later. Okay. All right, guys. Any questions? Any questions until this? A bit confusing. Okay, I admit that because of the names. But what do you do? Try to digest the names and look at the logic side of the material reacts in a universal form. When you are reducing the temperature, anyhow the material needs to cool down, right, from liquid to solid. So what are the microscopic transformation does the liquid is going through when it is cooling? That is what we have discussed so far. I think the one that is confusing is the names because it sounds very similar. So it might, poison your mind to be confused. That's what I'm guessing. So okay, guys, try to digest these, and next week we will finish up with topic 5. Okay, just a little bit more, and then we'll start with lecture 6, thermal processing and heat treatment, which is actually an addition to this. Okay, which is actually an addition to this. Both are very similar actually. Okay, guys.